Hello, my name is Eren Durham.
Hi, my name is Makhtar, and this is the Learning from Demonstration project overseen by Dr. Pereira and Dr. Dimas from the WVU Robotics RU.
This project is driven by the fact that the U.S. Census data shows that the farming population is decreasing, and that population is also aging. As a result, farmers may struggle to keep up with agricultural demands, as this already decreasing population may struggle with the physically strenuous activities that farming requires. Yet, farming is still essential because it feeds the world and keeps our economy running. Robotics researchers and scientists have proposed utilizing automated agricultural robotics to solve this problem. However, the question then becomes how to implement these systems, because farmers have spent decades and decades building up specific techniques to ensure that their produce is not harmed. So, how can these techniques be efficiently transferred to robotic systems? These techniques can be transferred to robotic systems through learning from demonstration, where a farmer demonstrates to the robot how to perform a specific task. This can be done through multiple ways. One method is to physically manipulate the robot itself, such as with this Franka robotic arm to the right. A farmer can physically maneuver the 7 joints seen in the picture to perform a task. Another method is to use a teleoperation device, where the human manipulates the robot with an external device. For our project, we use a device called the Jello, which was like a model of the larger Franka robot. In this video, you can see that while a person moves around the Jello, the Franka robot arm mimics every movement to pick up a pepper. The robotic system can also simultaneously save all the current states of the robot, such as the joint positions, velocities, and states. Once the data is saved, it can be input into an AI model to learn and interpret. Then, the AI model can understand and output exactly how to perform that task autonomously.
Let me walk you through our data pipeline, starting with how we teach the robot. We use a Franka Emika Research 3 robot arm, which we train through teleoperation. During each demonstration, we capture data from 2 viewpoints, a third-person view and a wrist-mounted camera, both using Intel RealSense cameras. This raw data goes through 2 parallel transformation paths. On the visual side, we record data as raw specs converted into HDF5 format, and finally into RODS, the standard format used for robot learning datasets. On the joint side, we capture the arm's movements over time and normalize them into a format that the model can consume. The visual data is then tokenized. Essentially, a CNN converts each camera frame into a set of observation tokens. Meanwhile, we take our language instruction, in this case, pick up the green pepper and place it in the bin, and run it through a language encoder to produce task tokens. All of these tokens, task tokens, observation tokens, and readouts feed it to the Octo transformer, which alternates between processing observations and producing actions through action heads. The end result, creating a model that identifies and is trained to harvest peppers autonomously. So, what's our actual methodology? First, we train the robotic arm to pick peppers using learning from demonstration, where a human demonstrates the task via teleoperation arm, and the robot learns to imitate that behavior. Second, our core research question. We study a diffusion-based visual learning action model and specifically look at how performance changes as we vary 2 things: the number of cameras used and the number of demonstrations required to fine-tune the model effectively.
After we implement this methodology, we expect that with 50 trials of demonstration and 2 cameras, the robot will be able to perform the task with maximal results and minimal parameters. We chose 50 trials because that is where accuracy frequently plateaus in recent literature, and we chose 2 cameras because we noticed that methods utilizing only 1 camera decreases the accuracy by around 25%. This semester, we have been able to set up the entire robotic system architecture, connecting components through TCP, serial interface, and ROS2 for communication between different devices. We were also able to implement the open-source generalist robot policy called Octo. We chose this model because of the versatility, documentation, and robustness. Octo can be trained on either goal images or language instructions with cameras or Pereira, and it can output either end effector positions by default or joint positions when fine-tuned. For our project, we chose to train the model with language instructions and cameras. Due to unsuccessful systematic controller implementations, we also transferred the output from end effector positions to joint positions. To fine-tune the Octo model to output joint positions, we collected a total of 102 trials of demonstration, with the robot picking up a single green pepper and placing it in a bin. To ensure robustness, the environment varied throughout the demonstrations. Finally, we were able to fine-tune the Octo model. We were able to deploy 2 different models, one trained on joint states and one trained on joint deltas. While neither of these models were successful, this project is ongoing and further work needs to be done to diagnose and understand the problems. Our expected results will help identify which parameters are essential for reliable robotic pepper harvesting systems. Additionally, all of our code is open source and accessible to anyone. This is important because there are already many barriers for this research due to the required expensive hardware. Publishing our data and code will foster growth among this field to continue to build on our work. Overall, these results will help lift the weight off shoulders among the farming population to ensure that the agricultural demands of today are being met while accommodating for the declining population through agricultural robotics.